Okay, time for just a little bit of math. Some of the mathematical properties of residuals and fitted values, and the correlation coefficient R. Let's say we're trying to predict some y value. There's some variability in the values for y. It wouldn't be an interesting prediction problem if y were always the same. There's also going to be some variability in the residuals, and it turns out that there are relationships between those. First, and this one's important, the average value of residuals is always 0, regardless of the original data, regardless of whether the association between x and y is really linear or not. This is a property of how we found the regression line in the first place. It's always a line where the total positive error is the same as the total negative error. And since residuals are just measures of error, if you take the mean of all of them, you always get 0. Any scatter diagram, not any line, but this is a property of the regression line. Now for the rest of the mathematical properties, it's actually easiest to describe them in terms of a quantity called variance. Variance is the standard deviation squared. So standard deviation is the root mean squared deviation. Variance is the mean squared deviation. The variance of the residuals is never any bigger than the variance of the y values that you originally started with. And it's usually smaller. How much smaller? Well, if you write down a ratio of the variance of the residuals to the variance of the original y values that you'd like to predict, that's always equal to 1 minus r squared, where r is the correlation coefficient. The variance of the fitted values, these are the heights of the line for every x for the regression line, is also always no bigger than the variance of y. And the ratio between the variance of the fitted values and the variance of y is r squared. Now you can put these two together and figure out that the variability of the values you're trying to predict, the y, are made up of two different quantities, the variance of the fitted values and the variance of the residuals. The way I like to think about this is that the total variability is the variability that's captured by the regression line. Since all these fitted values fall on the regression line, their variance is a property of that line. And then you have to add in the variance of whatever patterns you didn't capture by the line. This can be random noise, like it was in the case of parent and child heights, or this could be some nonlinear association, like it was in the case of the dugong. Whatever it is, this variance of residuals is what's left over once you've already accounted for the variance that can be described by a line. Now, if r is 1, then the line tells you everything there is to know about y. When the r is close to 1, the line tells you most of the information you need to predict y. And if r is near 0, then the line itself doesn't tell you much about y, and all the variance is in the residuals, meaning the errors that you would get when you make regression estimates are generally high when r is low. And the errors are low when r is high because all the variance is in the fitted values that are on the regression line itself. Let's apply these formulas to some of the data sets we've been exploring. So here we have a function to plot the fitted values. Here we see that the heights of the children are not tightly clustered around the regression line, but instead some of them are quite a bit larger and quite a bit smaller. For that reason, the correlation is not so high, it's only 0.32. Since this is closer to 0 than 1, that means most of the variability, most of the variance in the y values is in the residuals, not in the regression line. Therefore, if I compute the ratio of the variance of the fitted values to the variance of the actual heights, it's a pretty small number. This is r squared, which is what I'd get if I squared the correlation. Now, variance is just standard deviation squared. This variance is standard deviation squared. So if I take the same expression and I write NP dot standard deviation divided by the standard deviation of the actual y values, then I see the number r. So to reiterate, the standard deviation of the values that are the fitted values falling on the regression line divided by the standard deviation of the actual y values is the correlation coefficient. Is this a new way to find the correlation coefficient? Well, perhaps. But so far, in order to compute the fitted values, we computed the correlation coefficient in order to compute the slope of the regression line, in order to compute the fitted values. Now, if instead we had computed the fitted values using least squares, maybe we wouldn't have had to compute correlation beforehand, and then once you have the fitted values, you can always compute r using this identity. Now, this identity is basically just describing how much of the spread in the y values is accounted for by the spread in the fitted values. What about dugongs? That was a nonlinear association, and yet the ratio still holds true. When you look at the fitted values, we see that even though the association is not entirely linear, most of the spread in the blue values, which goes all the way from close to 0 to above 30, is described by the spread in the yellow values, which goes from below 0 to above 20. Here we see another reason why we're pretty sure that the association between dugong length and age is nonlinear, is that you can't have a dugong with negative age. That makes no sense. Really short dugongs are still a year old. Here's one more data set, hybrid cars. This is a description of different hybrids. Their price, the year they were manufactured, their acceleration, their miles per gallon, so that's how efficient they are, and their class. Are they a compact car or a two-seater, etc.? Let's see if there's an association between acceleration and their efficiency measured in miles per gallon of gas. It looks like there's an association, and if you draw a line through it, that line does capture quite a bit of the variability. The correlation in this case is negative 0.5, and the ratio of the standard deviation of the fitted values to the standard deviation of all the values is 0.506. So here's really the relationship. No matter what the shape of the scatter plot, the standard deviation of the fitted values is a fraction of the standard deviation of the observed values, and that fraction is the absolute value of the correlation coefficient. Why absolute value? Because really it's the square root of r squared.